The night sky looks close, but it is mostly distance. Light can cross Earth in 0.13 seconds, yet needs 8 minutes from the Sun. Past the planets, the scale stops feeling human. That is where the Voyagers are still moving. Voyager 1 and Voyager 2 are the farthest human-made objects ever built. They are not just far from Earth, they are far from the entire inner solar system. Their radio signals arrive faint and delayed. Their distances must be calculated, not seen. We measure their separation in astronomical units, or AU. 1 AU is the average Earth-to-Sun distance, about 150 million kilometers. Right now, photons from the Voyager antennas are still reaching Earth. We are listening to the past by hours, not minutes. Voyager 2 lifted off first, on August 20th, 1977. The plan targeted Saturn, Uranus, and Neptune, but the solar system offered a shortcut, using gravity like a moving ramp. That extra push would decide how far it could ever go. But a gravity assist is not just a slingshot. The timing must be perfect, and the margin is small. One wrong angle and a probe can miss a planet by millions of kilometers. So what did Voyager 2 gain at Jupiter? At Jupiter, Voyager 2 turned a detour into a scientific jackpot. It mapped the giant's atmosphere in detail, then swept past its large moons. The images of Europa and Ganymede were sharp enough to change planetary science, and it still had fuel in its trajectory. Europa looked like a cracked shell of ice. Ganymede showed grooves and older cratered terrain. From those patterns, scientists inferred something radical, liquid water hidden below. That idea still drives mission plans today. A moon can be frozen outside and active within. Then came Saturn, the solar system's most photogenic lab. Voyager 2 measured temperatures and magnetic fields while scanning the ring system. It also helped identify additional small moons, worlds only a few hundred kilometers wide. Each new object expanded the map of what Saturn controls. On January 24, 1986, Voyager 2 reached Uranus. It remains the only probe to ever fly past that planet. The data revealed dark rings, unusual moons, and a magnetic field tilted and offset from the planet's center. Uranus did not behave like a simple gas giant. And then Neptune rewrote the mission in a single pass. The probe was moving too fast to slow down. The gravity was about to bend its path out of the solar system's main plane. What did that final flyby reveal, and what did it cost? Voyager 2 arrived at Neptune on August 25, 1989. It confirmed that Neptune, like Uranus, has dark rings made of dust and icy fragments. It also captured winds and cloud structures on a world nearly 4.5 billion kilometers from the Sun. No other spacecraft has gone there since. Neptune's gravity redirected Voyager 2 away from the ecliptic. That ended any chance of new major planet flybys, but it opened a different target, the space between stars. From that new angle, Voyager 2 began sampling plasma, energetic particles, and the outer shape of the heliosphere. It became a boundary mission. Today, Voyager 2 sits about 128 AU from Earth. That is just over 19 billion kilometers, increasing at roughly 15.3 kilometers per second. These numbers sound enormous, yet they are tiny next to even the nearest stars. The probe is still inside our local galactic neighborhood's vast emptiness. Its future is slow-motion astronomy. In about 42,000 years, Voyager 2 should pass near Ross 248, a red dwarf about 10 light-years away today. Around 300,000 years from now, it should pass within 4.3 light-years of Sirius. Even the closest pass is still a wide miss. But here is the strange part. We call them the most distant objects, yet no telescope can simply point and see them. They are smaller than a car at distances measured in billions of kilometers. So how do we know where they are at all? We track the Voyagers by timing a whisper. The Deep Space Network sends a signal, then measures the return and the frequency shift. From that, engineers compute distance and velocity with extreme precision. Even at 19 billion kilometers, a stable radio tone becomes a ruler. The spacecraft stays invisible, but the math does not. Voyager 1 launched later, on September 5, 1977. Its main targets were Jupiter and Saturn, not Uranus and Neptune. Early images revealed Jupiter's storms, new moons, and even faint rings. The probe was built for a 5-year mission. It is still answering calls decades later. Io became Voyager 1's signature surprise. It showed active volcanism, the first confirmed beyond Earth. That matters right now, because it proves geology does not need sunlight to stay alive. Tides and gravity can heat a moon from inside. The solar system is still shaping worlds under our noses. At Saturn, Voyager 1 helped set the stage for its long departure. Later, from far out, it captured the famous pale blue dot view of Earth as a tiny point. That image is not romance, it is geometry. It shows how quickly planets shrink into pixels. The Voyagers are now far beyond that camera moment. But the most important discoveries came after the planets. In 2012, Voyager 1 detected abrupt changes in charged particles and magnetic conditions. The reading suggested it had reached the heliopause region, where solar influence fades. Scientists checked the data repeatedly. Were we finally seeing the edge of our star's bubble? The heliopause is a physical transition, not a painted line. Inside, the solar wind dominates. Outside, the interstellar medium sets the rules for plasma density and particle flows. Voyager 1's measurements matched that shift, making it our first direct sampler of near-interstellar space. It was still moving under the sun's gravity, but in new material. Now comes the definition trap. Crossing the heliopause does not automatically mean leaving the solar system. The sun's magnetic bubble ends around 120 to 160 AU, depending on direction and solar activity. Gravity reaches far beyond that, holding comets in a loose swarm. So a probe can be in interstellar plasma yet still be in the solar system. That swarm is the Oort Cloud. It is not a neat ring, but a vast, thin shell of icy objects. Estimates push its outer edge to around 50,000 AU, roughly 7.5 trillion kilometers. Voyager 1 will need tens of thousands of years just to reach its inner region. Leaving the solar system is a long calculation. After that, Voyager 1 has no scheduled destination. Its path is simply the leftover of launch energy and planetary gravity assists. In about 10,000 years, it should pass closest to the star Gliese 445, a red dwarf roughly 17 light-years away today. The pass will still be separated by interstellar distances. The probe will keep coasting, unchanged. But every message has a deadline. The Voyagers run on radioisotope thermoelectric generators, slowly losing power each year. Around 2025, the available energy falls far enough that instruments and transmitters must be shut down. When the last carrier tone fades, it will not come back. What does a silent spacecraft become? The power plan is careful triage. Engineers turn off heaters and instruments one by one to keep the transmitter alive as long as possible. Voyager 1 already shut down its cameras long ago. Each year buys a little more science from the edge. Then the probe becomes a powerless object on a stable trajectory, with no way to speak. If Voyager could look back with a camera today, the view would be underwhelming. The sun would appear only about 16 times brighter than the full moon in our night sky. The planets would be difficult to pick out from stars without long exposures. Space does not provide contrast for small, distant things. Distance is darkness plus scale. Even when instruments go quiet, the artifact still carries a message. Both Voyagers hold a gold-plated copper record with sounds and images of Earth. It includes greetings in many languages, nature recordings, and snapshots of human life. It is not a broadcast, it is a time capsule. The record will outlast every signal we ever received. It is fair to ask why we celebrate machines that will never arrive anywhere soon. The answer is measurement. The Voyagers turned points of light into mapped worlds, and hunches into magnetic fields, temperatures, and plasma readings. They proved hidden oceans were plausible, and volcanism could exist beyond Earth. They also drew the first real outline of the heliosphere's boundary. One day there will be a final packet of data. After that, only motion remains, 2 small objects drifting through the Milky Way's local environment. Their speeds are modest compared to starlight, but relentless over millennia. They will pass stars at wide distances, then continue on. And from far away, their story is simple. We learned how to ask space questions precisely.